Hi everyone, welcome to the fourth lecture. Today we'll be talking about optimization-based meta learning. Before that, a couple of reminders. Homework 1 is due on Wednesday, so a week from today. We're also going to post some project idea suggestions later today. This won't be enough, we'll hopefully have around 10 to 20 project suggestions, so I wouldn't necessarily rely on these to figure out exactly what your project should be, but if you want some inspiration, those should hopefully be helpful. Okay, so for today, we're going to just briefly recap some of the stuff that we talked about on Monday with the meta-learning problem statement and black box meta-learning methods. And then we're going to dive into optimization-based approaches to meta-learning. Kind of optimization-based meta-learning will be part of homework 2, so this should be pretty helpful for that. And so the goals by the end of this lecture are to try to understand optimization-based meta-learning techniques, including how to implement them, and trade-offs between black box approaches that we talked about on Monday and optimization-based approaches that we're talking about today. Okay, so to recap what we talked about on Monday, we introduced the meta-learning problem statement, which is to quickly learn a new task given experience from some set of previous tasks. And this is different from the multitask learning problem in the sense that you ultimately want to solve a new task. And this is a bit different than the transfer learning problem in that you are given data from a number of previous tasks. And in terms of the methods, we'll actually see that meta-learning methods actually optimize for transferability, whereas transfer learning methods don't do that. In general, in transfer learning and meta-learning, it's impractical to access the previous tasks when you're trying to learn the new task. Really, the dream is to be able to essentially be able to solve a new task very quickly with some parameters rather than having to iterate over all of the data from the previous tasks. In all of these settings, the tasks should share some structure. Otherwise, you're better off learning from scratch. Okay, we also looked at an example meta-learning problem, which was a 5-way one-shot image classification problem, where you're given 5 examples, basically a little mini training data set, and you want to be able to generalize to new examples using this training data set. And the way that meta-learning algorithms approach this problem is they assume that they have data from other image classes, and they structure these into train sets and test sets, and train a model such that after it sees the training data set, it can generalize to new examples. So these are the training classes, and then we use these to try to generalize to held out classes. And this was one example, but you can replace image classification with other machine learning problems. Okay, and then the last thing that we talked about on Monday was a kind of black box approach to meta-learning, where essentially what you do is you just pass in the entire training data set into a neural network, and that generates the weights or some low-dimensional context vector, and that's used to predict the label for new examples. And so the general form of these kinds of models is something that takes as input the training data set and a new example and is trained to output the correct label for that example. The pros of this approach is that it's a kind of very expressive neural network, very general form of representing a learning procedure. The downside is that it's a very challenging optimization problem to learn how to learn from scratch. So in this lecture, we're going to be talking about a different way to represent this kind of learning procedure rather than representing it as a black box neural network. And in particular, we're going to be thinking about actually representing this learning procedure as an optimization process with some parameters such that we can optimize the parameters of that optimization procedure to be able to perform well with small data sets. Okay, so exactly what this exactly looks like is instead of passing these data points into a data set, we're going to run some optimization procedure like gradient descent on our training data set. And this optimization procedure will have some free parameters. And so really the key idea of these optimization-based approaches is to try to embed an optimization inside the meta-learning process so that that optimization procedure does well. So overall, one question is, well, why might this make sense? Well, recall we saw fine-tuning last time as well. We saw that fine-tuning works pretty well. It doesn't work that well when you have a very small number of data points. But in general, it's already doing a lot better than learning from scratch. So essentially what we can try to do is, instead of running fine-tuning from a set of pre-trained parameters, we can actually try to optimize for a set of pre-trained parameters and other aspects of this fine-tuning procedure in a way that that fine-tuning procedure works well for small data sets. And so in particular, we want to just be able to run an optimization procedure at test time with our small data set. And what we're going to do is we'll take this fine-tuning procedure, and we want to optimize such that this fine-tuning procedure generalizes well to test examples. And so we want to take the results of this fine-tuning procedure and optimize for how well those parameters generalize to test data points. And in the simplest way that we could do this is actually to optimize this objective with respect to the pre-trained parameters. So we're going to optimize for a set of pre-trained parameters such that fine-tuning generalizes well with a small data set. And we'll be doing this over all of the meta-training tasks so that we were hopefully given a new task, that set of pre-trained parameters works well for new related tasks. So really the key idea here is to try to learn a parameter vector theta that transfers very well with fine-tuning, even when fine-tuning operates with a very small data set. Now, one way to visually depict this is something like the following. So say that theta is the kind of the initialization, the parameter vector that you're meta-learning, and maybe phi I star is the optimal parameter vector for task I. Then you can essentially think of it in some way as this illustration right here, where when you're at this point during the meta-training process and you take a gradient step with respect to task 3, you're quite far from the optimum for task 3. Whereas kind of at the end of the meta-training process, if you take a gradient step with respect to task 3, you want to be very close to the optimum for task 3, even if that gradient step is with respect to a tiny data set. Okay, so this particular procedure is referred to as model-agnostic meta-learning in the sense that it is agnostic to the model that you're using, as long as that model can be, it's kind of amenable to gradient descent-based optimization. Great, so a couple questions here. You might notice that there's one gradient step in this objective here. I'm writing that for simplicity. In many cases, actually, just a single gradient step can actually perform quite well. But you can also replace that with multiple gradient steps and optimize such that a few steps of fine-tuning works well. Yeah?
Curious about what's the space you call this picture is in the surrounding space?
Yeah, so the question is this picture in the parameter space? And yeah, so this is trying to depict like a 2D parameter space, essentially.
So my next question would be, what if the three laws from the three tasks, and like we can just for example for two objects, if one they have opposite directions, and so the next direction will be x and fixed at the point, and when you take the meta-learning step and the parameter will not change. Would that be possible?
Yeah, so you're wondering what if the meta-learning procedure ends up at a point that is the optimum for one of the tasks? And the gradient would be 0 in that case? Is that what you're asking?
Yes.
Yeah, so in that case, that's fine. The gradient will be 0, and then for that task, it will do well for that task. As long as it also can get to a good optimum for all of the tasks in your training data set, not just a single task. Yeah?
If we want to get to a data vector in this way, doesn't it assume that like each of the optimal phi's are kind of close together?
Yeah, so the question is, does this assume that the optimum are kind of close together in the parameter space? And one thing that I'll mention here is I think that this graphic is helpful for understanding the algorithm and visualizing it. But in reality, you won't just have a single optimum, good parameter that's good for that task. In reality, you actually have an entire space of parameters that is useful for that task. And especially as you move into higher dimensions, the kind of the space of optimal solutions and good solutions for a given task will get larger. So that's one thing, is that usually it's not just a single point. And then second, if you allow this to use a relatively large step size or use multiple gradient steps, that allows it to potentially move further in parameter space. That said, it is kind of implicitly making some assumption that there is a spot where you can get to a good performance for each of the tasks within a small number of gradient steps. And so that is some implicit assumption. In practice, we actually find that that assumption, or at least the algorithm, works well in a wide variety of problems. Yeah.
Sorry, just with that, but the goal of the algorithm is not necessarily to find like a theta that's already good at today's task, but to find a theta that such that with just a few number of additional steps can be good at any task that you give.
Yeah, that's a great way to put it. So essentially the goal of the algorithm is not to get a set of parameters that works well for all the tasks. Instead, it's to get to a space in parameter space such that you can quickly get to a good solution for each of the tasks. Yeah.
And then clarify, when you get a test task, you tell it when the training data for that test task with like a couple of small steps.
Yeah, exactly. Then, yeah, so when you're given a new task, then you just have these set of parameters, and then you can essentially just run fine-tuning, a few steps of fine-tuning. You could also run more steps of fine-tuning, potentially, if you have the compute. Yeah. Yeah, so in this case, you can have alpha just be a hyperparameter. You can also actually learn alpha as well, and we'll talk about that in a few slides. Yeah.
In this picture, it kind of looks like the best data is like an average of parameter space of models. Is there like a comparison of what sample things compared to just averaging different like estimates?
Yeah. So the question is, it looks like the optimal is just kind of almost averaging. It's not quite averaging, but in this picture, it looks like it's similar to averaging, and how does it compare to simply averaging good parameters? One of the things that actually makes averaging not necessarily perform well is that if you actually have a very large space of parameters that works well for each task, if you optimize each of them independently and then take the average, you may actually end up, like depending on where those optimizations landed, you may actually end up at a point that is actually potentially very weird and not very good in parameter space. And so in practice, averaging usually doesn't perform as well. Yeah.
And do we try with the learning method that our test and task, that we have some labels associated with that test to actually run that line tuning?
Yeah, exactly. So we're operating in the few-shot learning procedure where we have a small number of labeled examples, and we're running gradient descent on those labeled examples. Okay, I'm going to run through the algorithm, and then we can maybe get through some more questions. So if we recall the kind of approach for black box meta learning, we sampled a task, we sampled these data sets, we compute the parameters using our black box model, and then update the parameters data by kind of differentiating through that black box model. Really, the only thing that is different with the optimization-based approach is instead of optimizing the parameters by passing them through this black box neural network, instead we're going to be running one or a few steps of gradient descent. And that's basically it. That's the only difference from the black box approaches. So now there's a couple things that's worth mentioning here that you might notice. So the first is that we have a gradient here. We're trying to, we're kind of running gradient descent on our objective, on our meta objective. And there's also a gradient with respect to theta inside that objective. And as a result, this means that we are actually getting second order derivatives in this optimization problem. Because we are we have a gradient and we have another gradient, so we're taking the gradient of a gradient, which will give us a second derivative. And so you might be wondering, like, maybe we actually have to compute the full Hessian, which would be rather unfortunate because the Hessian will be, if you have a neural network of size with parameters, with n parameters, then the full Hessian will be n times n. And we don't want to have to compute something that's quadratic in our parameters. Another thing that you might notice is, well, what if we run multiple gradient steps in the inner loop? Does that mean that we'll actually get higher order derivatives, like third order derivatives? And so I'll run through kind of the answer to these questions on the whiteboard, but I'm curious if anyone has any initial thoughts on whether we need to compute the full Hessian or whether we need higher order derivatives. Any thoughts? Yeah?
I think the answer to the second question is no. Because yeah, when you're optimizing it in the yeah, I don't need to like necessarily take the gradient of the gradient there, like because the meta gradient is only happening in step 1, that's happening once, so I think that second order gradient happens in step 4, but not necessarily with multiple steps in step 3.
Yeah, so I can first go over through the second question, and the answer is indeed no. And the reason for that is that when you are computing phi I, when you're trying to kind of estimate the parameters for a task, if you run multiple gradient steps in the inner loop, then this is going to be theta minus the gradient of L of theta on the training data set. And then when you take the second gradient step, you're going to be taking that at the value of this. So if we refer to this as theta prime, then the next time we take the gradient, it will be, the second gradient step will be with respect to theta prime rather than with respect to theta. And then when you eventually need to differentiate all of this with respect to theta, you don't actually ever see there aren't any second order terms in here. And so when you need to differentiate theta through here, you only get second order terms coming up in terms of the gradient of the meta objective and no like third order terms, for example. Yeah?
I want to cheat a little bit because I heard in MAML where you use like some kind of like regularizer, like some kind of quadratic regularizer with that makes sure that phi is close to theta, and that makes like a closed form solution that doesn't need to use the full Hessian. So there's no conflict.
Yeah, so the suggestion was that there's an algorithm called MAML that I'll actually cover in several slides that can actually get away from using the full Hessian by using what's called the implicit function theorem. But I guess even for the original MAML algorithm, I'm wondering, not the MAML algorithm, even for the original MAML algorithm, do we need to compute the full Hessian? Yeah?
Can we use natural gradient?
So the question is, can we use natural gradient instead of Hessian? You might be close, but I'm not sure. You have a thought?
Oh, you could just ignore the Hessian.
You could just ignore the Hessian. You could throw away the second order gradients and derive a first order version of the algorithm. And actually the first order version sometimes performs surprisingly well, but that's not quite what I'm looking for. Yeah?
Maybe you can approximate the Hessian, like post order.
So you could try to approximate the Hessian. That would still not give you the kind of exact meta gradient, but it's definitely a valid solution.
Could you alternate which step you're optimizing for? Maybe go back and forth between the inner loop and the outer loop?
Do you think you have a procedure where you kind of alternate between the two? I'm not sure how exactly that would work. Okay, maybe I'll go through the answer. So, and actually this will involve a little bit of a digression. So one thing that's pretty cool that I didn't know about actually for until some time is if you have a Hessian, in many cases when you actually need to compute the Hessian, you only need to compute Hessian vector products. And so say you have some function f of theta, and then maybe let's use g of theta to denote the gradient of f, and let's use h of theta to denote the Hessian. In many cases, so computing the full Hessian is very nasty. But in many cases, we actually only need to actually compute what's called a Hessian vector product, which is basically the Hessian multiplied by a vector. And it turns out, as I'll show in a minute, you can actually, when you actually go about computing this, you don't actually need to compute the full Hessian. You essentially just need to compute a Hessian vector product. And there are much cheaper ways to compute a Hessian vector product than constructing the full Hessian and then doing a matrix vector multiplication. And one, I guess, with regard to the point of actually approximating the Hessian, one pretty cheap way to actually estimate this Hessian vector product is through something called finite differences, where you essentially do finite differences on the gradient of the function. And in particular, you can write this as being approximately equal to the gradient of the function evaluated at r times v minus the gradient of the function divided by r. So essentially, this is just doing finite differences on your gradient. It's comparing the gradient after the gradient at the function compared to the gradient at the function plus v multiplied by some r, and this becomes more and more accurate when r is small. And one of the things that's nice about this is that to compute this, you actually just need to evaluate the gradient twice. You don't actually need to actually compute the full Hessian. Now, this is an approximate way to estimate this Hessian vector product. There is actually a more exact way that doesn't have numerical stability. You might notice that there's an r here, and so if r is really small, you're going to get numerical stability issues. And so there's something called Perlmutter's method, which is named after Perlmutter, and that essentially gives you a way to do something like this, except in an exact way that isn't numerically unstable. Yeah?
These approximations are just kind of built into standard ML libraries like TensorFlow and PyTorch, like for second order computation.
Yeah, it's a great question. Does like TensorFlow and PyTorch already do this for you? And essentially do these approximation methods. And it essentially does. It uses, I believe it uses Perlmutter's method, which is actually an exact way that does something very similar to this, except in a way that essentially is just about as expensive as computing a gradient. And so in some ways, you don't actually need to worry about this at all, because PyTorch or TensorFlow will do it all for you. But I think it's useful to understand that when you're actually running this algorithm, TensorFlow and PyTorch doesn't need to actually compute the full Hessian in order to optimize this objective. Yeah?
And for the line above, we would apply then the chain rule, right? For the thing.
Yeah, exactly. So if our goal is to optimize, we essentially want to optimize the something like this, evaluated on d-test, which is equal to L of theta minus alpha grad theta L d train, evaluated at d-test. If we want to optimize this, we can use the chain rule, and it will essentially give us something. When we take the gradient of this with respect to theta, we will get something that looks like essentially dl d phi, evaluated at phi equals 1 minus alpha grad times d phi d theta. This is just using the chain rule. This is the gradient of the outside. This is the gradient of the inside with respect to theta. And this is just essentially the same as running backprop in the standard way through the neural network. And this is where things get a little bit more complicated. Essentially, if we want to evaluate the gradient of this with respect to theta, d phi d theta is, we take the gradient of the first thing, which is just I. and then we take the gradient of the second thing, which is equal to the Hessian. And so this is where the Hessian pops up. But fortunately, when we need the gradient of the entire expression, we get, this is a vector, this is a row vector, this is a matrix, and we get this expression times this expression. And so eventually we get a Hessian vector product from here. Yeah?
And you introduce the theta and like prime. And we have theta prime, we also have like an actual derivative of theta prime with respect to theta.
Yeah, so if you eventually have two inner gradient steps instead of one, this is the gradient of phi with respect to theta for one gradient step. If you have two, it ends up looking like the Hessian at theta prime of L times d theta prime d theta. And so this only has second order terms in here. We multiply this by the vector here. We actually get two Hessian vector products once we have two inner gradient steps. But we don't get any like third order terms, which is good news. Okay. Any questions on this? So to summarize, we have a nice way to compute Hessian vector products that requires, it takes about the kind of computation as taking one or two gradient steps. And then when we actually write out the objective, we get a row vector times a matrix. And this matrix includes Hessian terms. But luckily, we need to multiply this by this row vector. And that allows us to use this efficient Hessian vector method for computing the gradient of the meta objective. Yeah?
The last thing, that's if you take like two gradient steps.
Yeah, this is if you take two gradient steps in the inner loop. If you take three gradient steps in the inner loop, you'll have another term. And I should maybe double check that I actually did that right. Yeah, I think that's right. Yeah?
It's the same concept. Like you're using alpha for both.
Yeah, they don't need to be the same. And actually, there is a paper that showed that using different gradient steps for the two steps can be helpful, like a larger one for the first step, a smaller one for the second step. I'm just doing that for simplicity. Okay, so now how does this approach compare to the black box approach? We saw that at the algorithmic level, it just corresponds to running a different inner loop procedure for computing task-specific parameters. And so if we look at kind of the form of these two functions, one is one where we kind of pass in the data set into a neural network, and then the other is one where we essentially are running gradient descent on the training data set. And so in many ways, the general form is the same. Both of them are a computation graph that takes as input a training data set and a test input. But in one case, we're just passing all of that into a black box neural network. And in the other case, we're running gradient descent and evaluating the test input on the updated parameters. So yeah, essentially, MAML can be viewed as just a different computation graph that embeds this gradient operator into the computation graph, which is in some ways very similar to the black box approach. We're just building in some more structure about optimization into that learning procedure. It's also worth mentioning that you can potentially mix and match components of these computation graphs. And so, for example, you could learn the initialization, but replace the gradient update with some form of learned network, where you actually have like a network that takes as input a gradient step. And there's a paper by Sachin Ravi and Hugo La Rochelle that actually predates MAML that does something like that. Okay, in general, this sort of like computation graph view of meta learning will actually come up again in the next lecture when we talk about non-parametric approaches. Okay, now you might be wondering, when should we use one approach versus the other? One thing that's nice about embedding a gradient step into the optimization procedure is that it means that at test time, you're just running fine-tuning. And so regardless of what happens during the meta-training process, you're still running an optimization procedure that should get better at the test task. And so if you look at tasks that are extrapolated from the tasks that you saw during meta-training, these optimization-based approaches like MAML often do actually better than black box approaches. And so, for example, if you compare MAML with Snail and meta networks, which are two black box approaches, you can look at, say, like omniglot classification and look at the performance of the algorithm as you vary the test tasks, as you move them away from the distribution that they saw during meta-training. So for example, maybe we meta-trained on digits that are upright, and then we're evaluating on tasks where the digits are skewed. Then in this case, you see that performance deteriorates as you move away from the kinds of tasks that you saw during meta-training. But it deteriorates a lot less for a MAML-style algorithm compared to these black box algorithms. And kind of the intuition here is that if you're feeding in out-of-distribution tasks into a black box neural network, you don't really have any reason to expect it to generalize. Whereas if you're running gradient descent on out-of-distribution images, you can at least expect it to improve on the objective, just like fine-tuning improves. We can also look at something like the scale of the digits, and we see somewhat of a similar trend where MAML is a bit better at extrapolating. Yeah?
So how would you do actual inference with this? Like, before you can do inference, you need to do that fine-tuning, right?
Yeah, exactly. So what's happening at test time for the black box methods is it's passing in the support set into the neural network, whereas for MAML, it's taking the support set and running gradient descent on them. And these plots are showing the performance after using the support set to adapt to the task. Now, the other thing you might wonder is, well, okay, we're building a gradient step into this procedure. Does this mean that we are less, that the method is less expressive? Like maybe it can't represent the kinds of learning procedures that a black box neural network can represent. And one thing that you can show is that if you have a sufficiently large neural network, then the computation graph with a gradient descent step in it can actually still approximate any function of the training data set and the test input. And essentially this is saying that you can represent any learning procedure despite the fact that there's a gradient update in the computation graph. And this is under a few different assumptions. You need to assume that the learning rate is non-zero, of course, so that the gradient is actually having an effect. You need to assume that the loss function gradient doesn't lose information about the label. So this is true for loss functions like cross entropy and L2 loss. And you also need to assume that the data points in the training data set are unique. And this is interesting because this means that in some ways, MAML has the benefit of building in the structure or inductive bias of gradient descent compared to these black box approaches without necessarily losing the expressive power that you get from a a neural network representing a learning procedure. Yeah?
The loss function gradient to lose information about the data?
Yeah, so in some ways this is kind of more advanced material, but essentially if you view MAML as a computation graph that has a gradient inside of it, I guess essentially what I mean is that if you look at a loss function like an L2 loss function, then the slope, the gradient of this is actually changing, and you can figure out what point on this curve you are by looking at the gradient. Whereas if you have a loss function that is more like an L1 loss function, then in that case, if you look at the gradient, it isn't actually that informative about what the label is because the gradient is the same here as it is here and so forth. And so generally, if you use loss functions like this, you're going to have a less informative gradient update, potentially. In practice, MAML can still work with these, but if you need a very expressive update rule that maybe is a little bit different than gradient descent, these might not work as well. Okay, and then The last thing to mention on these optimization-based approaches is some of the challenges that come up and the ways that we can fix them. And this essentially will yield different variants of these optimization-based meta learning algorithms. So the first is that we do have this bi-level optimization procedure in the sense that there's an optimization embedded inside an optimization. And this in general can lead to instabilities. Yeah?
On the previous slide, you had the data points and the unique. Why is that?
Yeah, so the question was, why do the data points need to be unique? And essentially the reason for this is that if you want to be able to represent any learning procedure with respect to different copies of a data point, it's generally difficult to tell from the gradient how many copies of a data point you have. If you don't care about it depending on the number of copies, then it's generally fine. It's only a matter of like whether you want the learning procedure to do something different when you have like 5 copies versus 4 copies of a data point, which is usually not the case. Okay, so how can we get over the challenge of these like instabilities that might arise from the bi-level optimization? There's a few different approaches that have been used. One is when you have your inner learning rate, instead of having it fixed as a hyperparameter, you can essentially learn it. And this gives the algorithm more flexibility in how it chooses this optimization procedure. And one thing that you could do is instead of having it be a scalar function, you can have it actually just be a vector. You can have a different learning rate for each layer or a different learning rate for each parameter. And in general, giving it the flexibility to have different learning rates for different layers can be quite helpful because, for example, the biases of a network may want to have larger gradients than the weights of the network. Or maybe the later layers of the network want to change more, whereas the earlier layers of the network should change less. There are also some approaches that optimize only a subset of the parameters in the inner loop. You could optimize like just the last layer of the network, for example, or optimize like some multiplicative factors on different layers. And then one other thing that came up is like you don't necessarily have to have the same learning rate for each of the different steps. And so what you could do is you could try to essentially decouple the learning rate and other things like the Bostrom statistics for different steps in the optimization. And then there's also approaches that try to introduce some additional context variables into the network to try to generally increase the expressive power of this of the meta learning algorithm. And so really the takeaway here is that not necessarily to understand the details of all of these different approaches, but just to understand that there's a variety of simple tricks that can help improve the stability of the optimization. Okay, and then the second challenge that comes up is that you do have to backpropagate through this optimization procedure. And if you have one gradient step, that's not too hard. But if you have a lot of gradient steps, then optimizing through all of those gradient steps can be computationally expensive and also memory intensive because you have to store the optimization in memory. There's a few different approaches for trying to solve this, particularly in cases where you want to have a large number of inner gradient steps. One is to just ignore the fact that there are second order gradients. Just essentially, when you're computing the gradient, just crudely approximate this as identity. And this is not at all principled, often because this is not anywhere close to identity, usually. But in practice, it actually works surprisingly well on certain problems. On other problems, it doesn't work at all, but anecdotally, it can work for problems like few-shot image classification. And yeah, I'll leave it at that. Another approach is to only optimize the last layer of the network. And essentially what this is going to correspond to is optimizing for a representation such that if you train a linear layer on top of that representation, you can perform the task well. And there's a few different approaches that have done this, where they do like ridge regression or logistic regression on top of the features, or they do a support vector machine on top of those features. And it leads to, often leads to actually a fairly nice optimization procedure compared to the bi-level optimization that you see when you're kind of trying to backpropagate through gradient descent of the entire network. Great, and then the last thing that you can do is something else that was mentioned, which is to try to use what's called the implicit function theorem to derive the metagradient. And one of the things that's cool about this is you could actually compute the metagradient without actually differentiating through the optimization path by essentially using curvature information at the end of the optimization path. I'm not going to go through in detail how exactly you do this, because it's not something that's particularly intuitive, but if you want to learn more about it, I'd encourage you to, well, you can take a look at this paper. You can also take a look at what's known as the implicit function theorem. And you get some kind of interesting trade-offs in terms of memory and computation. So if you plot the number of inner gradient steps on the x-axis and the amount of GPU memory that you need, if you use the implicit function theorem, this stays constant, whereas it increases linearly for an approach that just backprops through the computation graph. And then the computation time also stays flatter compared to backpropagating through the entire procedure. And this purple line is the first order approximation, which also is a shallower line as well. The other thing that's kind of cool about this is it also allows you to do second order optimizers in the inner loop, because you don't actually have to do a second order optimization for the entire thing. And so it allows you to get kind of better performance in some cases by leveraging those second order optimizers. And the implicit function theorem is also useful for hyperparameter optimization as well. There's a pretty cool paper that essentially optimizes for data augmentation procedures using ideas like the implicit function theorem. Okay. And then lastly, the other thing worth mentioning is that you want to choose an architecture that works well. In general, the procedure is model-agnostic and should generally work well for a variety of architectures. But there is some work that actually tried to search for an architecture that works well with these kinds of algorithms. It actually found a pretty non-standard architecture and was able to get essentially like a 10% performance boost by actually optimizing for an architecture rather than using a more basic architecture. Great. So I'll summarize things, and then we can run through any more questions. So really the key idea here is we're going to try to get some task-specific parameters from the support set by running fine-tuning. And the approach constructs a bi-level optimization problem, and it has a positive inductive bias because you're essentially defaulting to fine-tuning. It also tends to extrapolate better by using the structure of fine-tuning. It's also maximally expressive if you have a sufficiently large network, and it is model agnostic, so it should be fairly straightforward to combine with your favorite architecture. The downside is that it typically requires a second order optimization, and this means that it can be compute or memory intensive. Okay, any questions on how things work or things that might be helpful? Or any questions on the math or anything? Yeah.
Can you explain again why it extrapolates better by the structure?
Yeah, definitely. So I guess one thing that I never really outlined is that, so I talked about this procedure where we sample a task, sample a support set and a query set, and then run gradient descent on the support set, and then optimize for the performance of those updated parameters on the query set. And then what happens at test time is you take the learned initialization, these parameters theta, and you just run gradient descent on them. And so if you're given a task that is completely out of distribution from what you saw before, at the very least, you are running gradient descent. You're running fine-tuning on that task. And so we can expect fine-tuning to already do fairly well on a variety of tasks. And so you should expect it to do at least as well as fine-tuning on out-of-distribution tasks. Now, in contrast with the black box approach, where you are passing the data points into a neural network, if you pass in out-of-distribution examples into a neural network, you can't really expect it to do anything reasonable, and it will probably do worse than fine-tuning will do. And so as a result, you can expect methods like these optimization-based meta-learning methods to do a lot better on out-of-distribution tasks than black box approaches. And this also relates to a question, I think, that from yesterday in terms of like the robustness of these methods as well. Yeah?
So I remember you mentioned earlier that usually like you only take one step during training, I guess to avoid overfitting. But at inference time, would you take like multiple steps or like convergence?
Yeah, it's a good question. So typically in the inner loop, you often use one step, mostly just for computational reasons. It can be challenging to backpropagate through a lot of gradient descent steps. It also seems to work pretty well. But then, like you mentioned at test time, computation is no longer a bottleneck because you're just running the procedure once and you don't need to backpropagate through it. And so in practice, it is pretty common to actually just run more gradient descent steps at test time. And that can perform well. And that can be especially helpful for out-of-distribution tasks for which you might need more fine-tuning compared to the small number of gradient steps that's optimized for the in-distribution tasks. Yeah?
Test time, so we do still update our parameters of test time, right? We would run the backpropagation, update them. So like using that on the phone where we only have like CPU and no GPU is pretty wouldn't work or would be super inefficient in our way.
Right, so at test time you're running fine-tuning, and the question was, it seems like that might be expensive to do like on a phone, for example, if you don't have a GPU. And this is where some of the algorithms that only update the last layer could be very helpful. And you don't necessarily need to have this inner loop step optimized to everything. Yeah?
I remember in the Michael paper where you do the other experiments, you use a neural reinforce for the inner optimization and the transversion possibility for the outer optimization. So I'm curious about why do you use reinforced by neural reinforce in the inner loop? Because my random guess is if you use TRQ for inner loop as well, and the computation will be much more intensive.
Yeah, so the question is, in a reinforcement learning setting, the MAML paper uses like vanilla reinforcer policy gradient. We'll get to reinforcement learning topics in several lectures, but the main reason is that the like an objective like TRPO does involve a kind of like a higher order optimization. I also think that PPO didn't yet exist at the time, but if something like that existed, then that would be a reasonable option as well. Yeah.
There's some intuition for why things like reptile, like first-order methods work well for certain spaces, or is that just virtue?
Yeah, so the question is, why do algorithms that, like first-order algorithms that throw away this, or reptile, which is very similar to this kind of first-order approach, why do they work well? I don't exactly know why they work well. I think it may actually have to do with the question earlier about how, like in some cases, it might be okay to just average parameters that work well. And I suspect that there are some cases where the kind of parameter landscape is nicely behaved, such that simple things like averaging gradients of different tasks performs well. In more complex scenarios, I have found at least that it can perform pretty poorly. These first-order algorithms can perform poorly. Yeah.
So they perform well. Are they performing better than if you did actual method with the second order derivatives, or is it just like slightly worse?
So when I say that the first order methods perform well, I mean that they perform about the same level as the second order methods on the simpler problems. Yeah.
I'm guessing given the RNN-based, or like the RNN-based learning approach might also have this problem, but I'm assuming it's step 3 over here that grading step, usually SGD is used, like a single example may be used from the task, but we just run into issues where the tasks kind of have large data sets where like doing just a single update or good enough of a step for grading the set might not be enough to kind of learn a good representation.
Yeah, so the question is, for these inner gradient steps, I assume you mean step 3, not step 4, right? Yeah. What if you have a large data set? Are you using SGD here or something else? And typically, actually, in most cases, these algorithms are applied to few-shot learning problems where you have a relatively small data set. But actually, this inner gradient step is often computed with respect to all of your data points, not just one data point. And if you have like 100 examples, that allows you to compute a gradient that depends on all the examples rather than just one. Yeah.
So you're saying that it's often a good idea to just do one grad step and then do for computational reasons, but it's also a good reason to just prepare it to be able to adapt with one grad step at test time. You have access to more grad steps and it just becomes easier. So the training setup is harder than the test setup. Right.
So you're asking, does it make sense? Using one gradient step in the inner loop, does that make it harder?
Make it easier at test time, which you have access to more grading steps at test time. But you're preparing it to just adapt with one grading step.
Yeah, so the question is, by meta training with one gradient step and meta testing with more gradient steps, does that essentially make it easier at test time? And yeah, I think so. I think that that essentially encourages it to learn very quickly. And when you actually have a longer optimization problem at test time, that makes it a little bit easier. But the network should still be able to learn quickly because of the one inner gradient step. Okay, one more question.
There's a question in chat that says, is it good if feature reuse and not only the first order approximation relationship as Hessian?
Yeah, so the question is it because of feature reuse that the kind of first order method works better, works well? I think it could have to do with feature reuse, although I think that the concept of feature reuse is a little bit vague in some ways and not as precise, but I think it could, especially in computer vision problems. Okay. So now I'm going to run through a case study, and I think that this should be pretty helpful because so far we've only seen like image classification problems where we're trying to classify a category of an image. And we'll look at a case study that is a bit different than that example, and it'll hopefully illustrate the generality of these kinds of meta-learning methods. And so in particular, this paper wanted to be able to predict land cover. And this can be useful for essentially trying to monitor how the Earth is being used over time and can be used for various conservation efforts or urban planning or other things. And it was at the kind of Earth Vision workshop in 2020 at CVPR. Okay, and so the problem is they want to map land cover from satellite images. Satellite images are relatively cheap to get. Getting land cover annotations through on-the-ground surveys is a lot harder to get. And so they looked at a couple different data sets. One is a data set right here, where you have very low resolution, high-level segmentation of the land cover. And the second example is one that actually has a much higher resolution land cover segmentation. And I'm showing the different classes here. So like blue corresponds to urban regions, green corresponds to forest regions, and so forth. And this has applications in kind of urban planning, climate change research. And it has a number of challenges. So labeling data like this is super expensive because you need a label for every region of pixels. And different regions also look different as well and have different land use proportions. And so they want to be able to frame this as a meta-learning problem. And as an example, they have examples of croplands of 4 countries. This is kind of illustrating the kind of differences that you see in different regions of the world. And different tasks are going to correspond to these different regions of the world. And so hopefully we'll be able to leverage a lot of annotated data from some parts of the world to be able to be able to segment images from a new region of the world with only a small amount of data from that region. And so you can kind of, this is a graphic from the paper where they are trying to run this kind of meta-learning process such that it allows them to quickly adapt to different regions of the world and learn a model that can segment land cover in those different regions. Okay, so first we'll look at this SEN1MS or SEN12MS data set. And they had different kind of geographic metadata. Here's some examples of the images, and they're using the blue data points for the blue regions for meta training, the light blue regions for like validating and tuning the hyperparameters of the meta learning algorithm, and then the orange for actually reporting results and evaluating. And so, as an example of a two-way, two-shot classification problem, they have an illustration here where they are trying to classify, for example, forest versus croplands. And they have kind of, the samples correspond to these different regions of the world with labels. And so they'll have K regions that are labeled, and they'll provide that to the algorithm. And then they want to be able to predict the land cover for other parts of that particular region of the world. Okay, so that was the first data set. They also looked at this deep globe data set. Unfortunately, this data set didn't have any geographic metadata. It didn't actually have like coordinates corresponding to where the satellite images are coming from. And so they had to roughly guess from the metadata. And they used clustering to do that. And then what the few-shot learning problem looks like is they're given kind of one part of a region of the world, and then they want to be able to evaluate and make predictions for the land cover in other regions, or other parts of the same region. And so this was the data set that had also much higher resolution data sets, and so ultimately they want to be able to predict the labels that look like this. Okay, so they had meta training data, and at meta test time, they're given a small data set for a new region. And this is kind of the support set of the meta test task. And they compared just randomly training on the support set of the target task. So this is just training from scratch on the support set for the test task. They also compared to pre-training on all of the meta-training data and then fine-tuning a network on the data from the target region. And then they also evaluated model-agnostic meta-learning on the meta-training data and then adapting with a small amount of data on the target task. And so the results for the first data set are here. And they're plotting the performance with different numbers of examples in their support set for the test task. And what they find is first, random doesn't do very well. They see a significant performance improvement from using a pre-trained network. And then they also see a pretty big performance improvement, I think around 10 to 20% when using meta-learning compared to using a pre-trained model. And then on the deep globe data set, they found that MAML and a pre-trained network perform somewhat similarly when they have a random split. But then when they make it, when they give it a clustered split, which is harder, and you have to adapt to regions of the world that are probably different from what was seen during meta training, you see a much larger gap in performance. Great. And there's also more visualizations and analysis in the paper. This is just kind of a subset of the results. Any questions on the case study? Yeah.
Why the accuracy level is even slower than accuracy for random guess at zero shot?
Yeah, so the question is, why is this kind of below the performance of random guessing? The reason is that in MAML, you're optimizing for the performance after fine-tuning. And so the pre-fine-tuning model, it might always, like, you're not actually optimizing it for it to be good in any way. And it may actually be, like, arbitrarily bad unless you actually tell it to that it should actually be good. And so you can actually one thing you could do is you could actually optimize both for this objective as well as like the objective of the original parameters as well. And that's useful if you care about the performance of the model before fine-tuning. Yeah?
There's a question. Is there a comparative example against the black box meta learning algorithm?
Yeah, so I don't think that they compared to a black box meta learning algorithm in this paper. I would expect it to not perform as well, especially in settings where, like, as we saw before, the held out regions, different regions of the world look quite different. And so in some ways it is somewhat out of distribution. And so the black box methods probably wouldn't do as well in this sort of scenario. That's why they didn't evaluate it. And so I don't know for sure. Yeah.
These metric and when they were splitting the data between meta testing and meta training, so was there any metric to ensure that there's no covariant shift in data or within to it actually attempt when they're picking up two environment points?
Yeah, so here.
When they're picking which points to be part for testing and which points to be associated with learning, was there any metric on trying to reduce covariant shift and what they think it or they think to it?
I believe that they randomly sampled the locations, and that should mean that there's hopefully less covariate shift, less distribution shift than you would otherwise. Okay, great. So that's it for today. We covered optimization-based meta learning. We talked about how it differs with these black box approaches, as well as some of the challenges and different ways to tweak the method to address those challenges. And then we also saw a case study of land cover classification. Yeah, and then in terms of kind of a roadmap for what we're going to be seeing next, so far we've covered black box meta learning and optimization-based meta learning. And there's one class of meta learning methods left, which is called non-parametric methods. And so on Monday next week, we're going to cover these methods and also just kind of compare all the approaches from a high level. And then on Wednesday, we'll look at some more advanced topics, but that are quite important for thinking about the performance of meta learning algorithms and should have some important implications if you choose to use some of these algorithms for your final project. And then on Monday of the following week, we're also going to cover the kind of Bayesian interpretation of meta learning algorithms. And then on Wednesday of week 4, we'll start covering reinforcement learning. There we go. Following Monday is Bayesian meta learning and then reinforcement learning. Also, project proposals will be due on, I think, Wednesday of week 4. And so it's good to start thinking about your projects now. And so hopefully some of the project idea suggestions that we'll post will be helpful for that.